Hi everyone, my name is Iri, I'm a developer, and today I'm going to show you how to build the convolutional neural networks. Why do we actually need this? Because regular neural networks completely fall apart when it comes to images. One image, 200 and 200 pixels, can have like 120,000 values, and if we feed it to the regular neural network, we're gonna have like tens of millions of parameters. And this model becomes massive, slow to train, and overfits easily. But the real problem is regular networks treats every pixel independently. They have no concept of spatial relationship. Convolutional neural networks solve this. Instead of connect every pixel to every neuron, they use small filters that slide across the image looking for local patterns like edges or textures. The same filter is reused everywhere, so the network learns if I see this pattern, it matters regardless of where it appears. This makes CNN perfect for any task involving images, especially when we talk about some medical tasks, about analyzing X-rays and MRI scans, which we're gonna do today. So today we're breaking down how these convolutional layers work and gonna build one from scratch. Okay, so we are working with brain MRI scans and we need to automatically detect and classify different types of tumors. This is a classic image classification problem with 4 classes. And we have 4 categories in our MRI images data. It's glioma, meningioma, no tumor, and pituitary tumors. Let's start from the very beginning. First, we import PyTorch, our deep learning framework. Torch and TorchNN give us the neural network building blocks. Torch Optim contains our optimizers, the algorithms that update our model weights. Data loader and dataset are for loading and managing our image data. Torch Vision Transform. This is crucial. It handles all our image preprocessing and augmentation. Then we import NumPy for numerical operations. Peel, the Python imaging library. This opens and processes our images. OS help us navigate file paths. Scikit-learn gives us the classification report for evaluation our model. And TQDM, this creates those nice progress bars during training, and you will see it when you try to test it. And okay, let's go to our configuration. These are our hyperparameters. Batch size equals 32. This means we'll process 32 images at once during training. Num epochs equals 25. We'll go through the entire dataset 25 times. Learning rate is 0.001. This controls how big our optimization steps are. If this is too big and then training becomes unstable. If it's too small, then training takes forever. So this is like a normal rate. Image size is 224 by 224 pixels. We'll resize all brain scans to this size. And num classes is 4. It's our glioma, meningioma, no tumor, and pituitary. Then we set our device to CPU. If you have a GPU, change this to CUDA for much faster training, but I'm gonna test it on, I tested it on my Mac, so I used the CPU. And train dir and test dir, you can see it here, but these are empty strings now, so you need to add your dataset paths here. After you download this dataset, you will find the link in README file in GitHub in the description of this video. So now we create our custom dataset class. This inherits from PyTorch dataset. The init method initializes our dataset, and we store the data directory and transforms. Then we create 2 empty lists, one for image paths, one for labels. And this dictionary maps each tumor type to a number. Glioma is 0, meningioma is 1, no tumor is 2, pituitary is 3. PyTorch needs numbers, not strings, so this conversion is essential. Now we loop through each class in our dictionary. For each class, we build the full path to that class folder, and then we initialize a counter for images in this class. Inside, we loop through every file in that class folder. We check if the file ends with JPG, JPEG, or PNG, because we only want image files. If it's an image, we append the full path of our images list, and we append the class index to our labels list. We increment the counter, and after scanning all folders, we print how many total images we found. The len method returns the total number of images. PyTorch needs this to know how big our dataset is. And getItem is called every time we load a single image. We get the image path and label at the given index. We open the image and convert it to RGB. This ensures all images have 3 color channels. If transforms are provided, we apply them to the image. And finally, we return the processed image and its label. Now our data augmentation pipeline for training. First, resize to 224 by 224, and this makes all images the same size. Then we use random horizontal flip with probability 0.5. It flips images left to the right randomly. This helps the model learn that tumors can appear on either side of the brain. And random rotation by 15 degrees. Slight rotation simulate different head positions during MRI scans, which is also very important. Color jitter. We randomly adjust brightness, contrast, saturation, and hue. This simulates different MRI machine settings and lighting. ToTensor converts the peel image to a PyTorch tensor. And we normalize with these specific mean and standard deviation values. These are ImageNet statistics and help training converge faster. For validation and testing, we keep it simple, just resize to tensor and normalize. And we don't do any random augmentation. We want to evaluate on clean, consistent data, so we just use this. Okay, so this block only runs if we execute this file directly. We create our training dataset, pass in the training directory and training transforms. We create our test dataset, pass in the test directory and validation transforms. And we split the training data 80-20. Train size is 80% of training dataset and the validation size is the remaining 20%. Random split divides our dataset. We use a fixed seed of 42 for reproducibility, same split every time. And we print a number of training and validation samples to verify our split worked correctly. Here, now workers equals 0. This means single-threaded data loading. Increase it if you have multiple CPU cores. And pin memory is false. That set this to true. If you are using a GPU, it speeds up the transfer. We create the training data loader. Batch size of 32 means we load 32 images at a time. Shuffle is false here. Normally you'd set this to true for training to randomize the order. And we print how many batches per epoch. This tells us how many update steps per epoch. And same process for validation and test loaders. For validation and testing, shuffle should always be false. We want consistent evaluation. And we print final statistics, total samples in each split and number of classes. Okay, so now the neural network architecture. We define our class, inheriting from NN module. The init method builds the network structure. First convolutional block. 3 input channels for RGB, 32 output feature maps, free and free kernel, pairing of 1 to maintain spatial dimensions. Batch norm 2D normalizes the 32 feature maps. This stabilizes training. ReLU activation, it adds nonlinearity. Max pool 2D with kernel 2 and stride 2. This halves the spatial dimensions. Dropout of 25%, so it's like drops 25% of connections during training to prevent overfitting. All of other layers, like first 4 layers, almost the same, but on the layer 2 we take 32 channels and output 64. On the third one we take 64 and output 128, and on the fourth we take 188 and output 256. So it's like structure is the same, and each layer like this learns progressively more complex features. After 4 pooling operations, our 224 on 224 image becomes 14 for 14. 256 feature maps times 14 times 14 equals our flattened sides. And FC1 is fully connected layer with 512 neurons. Dropout is 50%. It's very aggressive here because fully connected layers overfit easily. So we add here more of dropout. And final layer outputs 4 values, 1 for each class, because we have 4 classes, as you remember. The forward method defines how data flows through the network, pass through convolution layer 1, 2, 3, 4 in sequence. Then XU flattens the output, converts from 4D tensor to 2D. ReLU activation on FC1 output. Apply dropout. And pass through FC2. This gives us our final class scores. Then we return the output. And we create an instance of our model and move it to our device, CPU in this case. Cross-entropy loss function. It's perfect for multi-class classification. It combines softmax and negative log likelihood. And ADAM optimizer, adaptive learning rate optimization. We pass our model parameters, learning rate, and weights decay for L2 regularization. Reduce cell learning rate on plateau scheduler. If validation loss doesn't improve for 3 epochs, reduce learning rate by a factor of 0.5. And this helps fine-tune the model as training progresses. Our training function for 1 epoch. Model train puts model in training mode, enables dropout and batch norm updates. Initialize running loss, correct predictions and total samples. Loop through batches in the data loader. Move images and labels to device. And optimizer zero grad, just clear previous gradients. Forward pass get model outputs. Calculate loss. Loss backward is computing gradients. Optimizer step is updating weights. Accumulate running loss. Torchmax get the predicted class, the one with highest score. Count correct predictions. And every 10 batches reprint current loss and accuracy. Then we calculate epoch loss, total loss divided by number of samples, calculate epoch accuracy, correct predictions as percentage, and return both metrics. Validation function is very similar to training. We do model eval, puts model in evaluation mode, disables dropout. Torch no grad, don't compute gradients, saves memory and computation. We don't need to compute gradients on evaluation. Loop through validation data, calculate predictions, accumulate loss and accuracy, return validation loss and accuracy, and then training preparation. So we create empty lists to store metrics across epochs, initialize best value accuracy to 0, loop for num epochs. In this case, we had 25 epochs in the beginning in our hyperparameters. Print current learning rate, because as you remember also we scheduling it, so we reduce learning rate if we get the plateau. And then call train epoch. This trains for one full epoch. Call validate this evaluates on validation set and append metrics to our lists. Print training loss and accuracy, print validation loss and accuracy. If not the first epoch, calculate changes from the previous epoch. Print how much train loss changed, print how much validation accuracy changed. Score old learning rate. Call schedule step with validation loss to get new learning rate. If it decreased, print the change. If current validation accuracy is better than best so far, save the model weights. Update best validation accuracy. This ensures we keep the best model, not just the final one. Evaluation function for test set. Model eval for evaluation mode. Create empty list for predictions and true labels. Loop through rest data with no gradient computation. Get predictions, extend our lists. Return predictions and labels as numpy arrays. And we call evaluate model on test set, calculate test accuracy, print test accuracy, and define class names for readable output. We print classification report. This shows precision, recall, F1 score for each class. And this tells us exactly how we are performing on each tumor type. And that's it. A complete deep brain tumor classification system from scratch. Try to take your time to build it by yourself, experiment with different hyperparameters, and see how the model performs. You can find all the links in the description, and if you have any questions, feel free to ask them in the comment section. Thank you.